Hi everyone. Can you hear me?
Yes, sir.
Okay. So welcome to the sixth session of analog electronic circuits. So we will solve some questions that may help you solve this week's assignment. So let us start. So uh, so in this question we have a differential pair and they have a common mode voltage VCM applied to both of the inputs and it is 1.7 volts. I naught is given, RD is given, VT is given. What is the minimum allowable supply voltage if the transistor must remain in saturation? Okay, so for this we have to apply the condition for saturation in this circuit. Then we can find VDD. So let us solve this. Let me take this. Okay. So what we are given? We are given VCM is 1.7 volts. I naught. This I naught is 3 milliampere, and RD is given as 0.633 kilo ohms. And threshold voltage VT is zero point 0.5 for both the MOSFETs. So these are both NMOS, as we can see here. So this is drain and source, drain and source. Okay. So if so, both these branches are identical. So if 3 milliampere current is flowing here, so 1.5 milliampere will flow from this branch and 1.55 milliampere from this branch, right? So okay, let me write 1.5 milliampere here also 1.5 milliampere. Okay. Now let us see. Let's see this transistor and let us apply condition for saturation. So for saturation, VDS should be greater than equal to VGS minus VT, right? So okay. So this is an ideal current source, right? So we can assume the potential drop across it to be zero. So I can assume VGS to be VCM for this part. Okay. So VDS is greater than equal to VCM minus VT, and VCM is given 1.7 and VT is 0.5. So VDS is greater than equal to 1.2 volts. We have one condition now. So let us take it equal. VDS equal to 1.2 volts. Now let us apply KVL in this branch. VDD minus ID RD minus VDS equals to 0. So VDD equal to VDS plus ID RD. So this here the drop will be ID RD and here it will be VDS. So VDS is 1.2, ID is so ID will be 1.5 milliampere. 1.5 milliampere into RD is 0.633 kilo ohm. Only 1.2 plus 495. So VDD is 2.149 volts. Yeah. So is there any doubt in this question?
Sir, how
No,
can
sir.
we assume that the voltage across the current source is zero?
Sorry, can you repeat?
See, sir, you told that across the source and ground, the voltage is zero. Right? Based upon the assumption
Yeah,
only, we solve that problem, right?
yeah.
Uh, how can we justify that the voltage across the current source is zero?
Okay, let me see then. Let us see if we can solve it if we consider some drop. Okay, I'll try again. So VDS should be greater than equal to VGS minus VT, right?
Yes.
So let's say this node is VD and let's say this is VS. Okay. So VD minus VS is greater than equal to VG is VCM minus VS minus VT. So we cancel this. VD is greater than equal to 1.2 volts, and we can apply case. Okay, yeah. If we apply uh, KVL here, so VDD minus ID RD equals to VD. So VDD equals to 1.2 plus 1.5 into RD. Yeah. So yeah, you are correct. That was my mistake here. Let me clear it. I'll write VD. Yeah. You are right. We cannot assume it to be zero. It will be. I was confused. It will be actually zero for AC case because this is an ideal current source. It will not allow any change of any small signal current here. So for AC, it will be a ground, but not for DC. You are right.
Okay, sir. Okay.
Anything else? So answer will be this only. Yeah. Anything else in this part?
Everything is clear, sir.
Okay. Thank you. Let's move to next. So in this question now, what do we have to find here now? So we have same values as previous. VDD is given 5 volts. KN and everything is given. What is the maximum input common mode swing that is allowed? Okay, it's a good question. I'll just paste the circuit again because it is the same circuit. So uh, what they are saying is, so if we see this, this part, Kn of the input device is 33 millisiemens and Kn of the device used to make the current source is 66. So what they are saying is we have another device here that is acting as an current source, right? So let us assume there is an NMOS and its Kn is given 66 millisiemens per volt, and Kn for these are 33 millisiemens per volt. So let me just write it. VDD is 5 volts. I naught is 3 milliampere. RD is same 0.633K. V5, and let me say this. Let's say this is 5, this is 2, and this is 3. So Kn1 equals to Kn2 equals to 33 millisiemens per volt. Kn3 66 millisiemens per volt. Okay, so what do we have to find is now the maximum input common mode swing. So what they're saying is uh, what is the maximum change in this VCM that we can apply so that this circuit still works. So they are talking about swing, right? So we have to find the maximum minus minimum swing. So there is a term for this. This is called ICMR. It's called input common mode range. So what it means, like what is the range of VCM that I can apply to bias these input transistors so that this circuit works. So ICMR is given as VCM max minus VCM minimum. So the task here is to find these two maximum and minimum values. Then we can find the ICMR. So anyway, so we will use the basic equations only to find these conditions where the circuit remains in saturation. So to find these, we have to apply two conditions. One is the saturation condition, where VDS is greater than equal to VGS minus VT. And second is the current carried by transistor. So if I naught, if let's say I naught is there, so I naught by 2 will flow here, right? So I naught by 2 current should flow through these two transistors. So that is the second condition we apply. So one of the conditions will give us this and other condition will give us this. So let us try to solve this. So let us apply the first thing. VDS is greater than equal to VGS minus VT. Saturation. So let us take this transistor drain source gate. So I can write VD greater than VG minus VT again, and VD is okay. We don't know VD or not. Okay. So here, let me just write VCM minus VT. VD should be greater than VCM minus VT. So VCM should be less than equal to VD plus VT. So it gives me an upper bound on VCM, right? So it is VCM max equal to VD plus VT. Now what is VD here again? So VD is nothing but VDD minus IDRD plus VT. This is VCM max And the second thing, so this will give us uh, one of the condition. Next one is the current condition. So for that, current I naught by 2 flows through this branch. Can you please mute Venkata? Can you please mute yourself? I think there's some background noise. Yeah, thank you. So for this current I naught by 2 should flow through this, so it should be Kn Vgs minus Vt whole square, right? So Vgs minus Vt equal to under root I naught by 2 Kn of 1 constant Kn 1, and let us say, let us assume that, let's say this voltage is Vx. Okay. So Vx is nothing but okay, so we have a transistor here right now. So Vs is nothing but the overdrive voltage of this transistor. Let's say transistor 3. So it is VO3. So that is the minimum. VO3 is the minimum voltage that is required to keep this sink transistor into saturation, and we have taken that as Vx or VO3. So if I rewrite this, so Vg minus Vs is Vx, or let me just put VO3. VO3 minus Vt. Okay, let me just write Vx only. For Vx minus Vt equals to, and what is this? So this is actually VGS minus VT. So this is the overdrive of transistor 1. So let me write here VOV1 equals to under root I naught by 2 Kn1. Right. VO1. So the minimum VG min will depend on minimum Vx. Vx min plus Vt plus VO1. And Vx min is VO3 plus Vt plus VO1. So if we consider, so VO is actually okay. So the overdrive that we want to give in our circuit is actually in our control, right? So this overdrive is what VGS minus VT. So this, for this transistor, the VG is in my control. This is the uh, current source, and I can apply whatever VG I want. So I should keep this apply VG such that this voltage drop is minimum to get the minimum condition here. So that is why I had written Px min here. So if we apply this voltage drop here also, so it will be 2 VO plus VT, VG min. So I can write it as VG min is nothing but VCM min. I'll write VCM min 2 VOV plus VT. Okay. Now what is VOV? So 2 VGS minus VT plus 2. So for the sink transistor, so if I naught current is flowing here, so VOV will be under root I naught by Kn. It was transistor 3, right? So Kn3. So in this way, we have both the conditions of VCM min and VCM max. And our ICMR that is we have been asked is VCM min, sorry, VCM max minus VCM min equals to VDD minus IDRD minus VT minus 2 VOV minus VT, VDD, IDRD. minus 2 VOV minus 2 VT. Okay, so we know all these values. We can solve it. So I'm not going to solve it right now. You can solve it. But yeah, answer will come from here only. Any doubt in this part?
So what is the VOE value, sir? It's Vx, right?
Sorry, what is VOV?
Yeah, it's Vx, right? Voltage
Yeah,
Vx.
VX, yeah, VX we consider it here. It is same as VOV. And we can find it by this. We know the current I naught through this. We also know the Kn of this device. It was 66 millisiemens per
Yeah, yes,
volt.
sir.
So we can find this VOV and we can put it here and we will get the ICMR.
Okay, sir.
Anything else? Should we move ahead?
Yeah, we can move it.
Okay. So next question is this. Okay. So in this question, what do we have to find? We have to find R such that the gain is given. Okay. We have been given AD, we have to find R. So let us take this, copy this. Okay. So first, they have given AD. AD is what? 34.7. So what is AD? AD is the differential gain, right? So if I apply, let's say, plus VD here and minus VD here, so the difference between these, the voltage at these two terminals is the output. So AD is, let us say this is VO1, this is VO2. So AD is VO1 minus VO2 divided by 2 VD because I'm applying this and this both here, right? Okay. Okay, so let me do it other way. Let me apply. Let me see this. Let's say plus VD by 2 here and minus VD by 2 here. Then we will get VD. So this is the gain. Okay. Anyway, so this gain. So if we see, this is also uh, similar to what to say a common source amplifier, right? So we apply input here, we take output here. So AD is nothing but the effective GM into Z out, and so GM will be what? GM will be of this. GM will be of this transistor where we are applying the input, and Z out we can calculate at this node. So for Z out, let's say I'll just draw it like this here. So let us, we have our output at this node. So for Z out, we need to see out Z out here. So Z out will be this parallel with this. Let's say 1 and 2. So in one, let's say Z1. Z1 will be nothing but let me say RO, right?
GMB
RO,
plus
sorry,
1 by GMB plus GDS.
yeah, GMB plus GDS you are saying, no?
Yes, sir.
So GMB is not given, so I'll ignore that. Let's say GD, I'll write it GDN. This is an NMOS here, and above one is PMOS actually. So let's say it has GDN, it has GDP, and okay, one more thing. KN is 2.9, KP is 2.2 milliseconds on derivative. Okay, so what is GD? GD is equals to lambda ID, right? So ID is same ID is flowing through this branch, ID by 2, I naught by 2. So GDN will be equal to GDP into lambda ID. Okay. So anyway, so Z1 is 1 by GDN, Z2 is now parallel of these two. So here it will be 1 by GDP parallel with R. So Z2 is 1 by GDP parallel with R. And Z0 is Z1 parallel Z2. That is 1 by GDN parallel 1 by GDP parallel R. Okay, so let us find this value. GDN lambda is 0.1. Lambda is 0.1 per volt. ID is I naught is 0.16. So ID will be 0.08 milliampere. So 0.08 milliampere. 1008 millisieverts. GD. So Z out is 1 by GB and parallel with 1 by GBP parallel with R. So 1 by 0.008 parallel 1 by 0.008 R. It is in milli. So we solve this, it will be 125 kilo parallel with 125 kilo parallel with R. So the parallel of these two will be the half of these, right? R parallel R is R by 2. So it will be 60, how much is it? 62.5 parallel with R. Okay, so AV is what? GM Z out. So AV is 34.7 equals to, and GM, okay, GM we also need to calculate. So let us first find GM. GM equals to uh, 2 KN VGS minus VT. We can write it as 2 Kn under root ID by Kn, 2 under root ID by Kn, 2 under root 0.008 milliampere into Kn is what? 2.9 milli. 2.9. So if we solve this, we should get 0.963 millisiemens. So it will be 0.963 millisiemens into 62.5 parallel R. This is in kilo ohms, this value. Okay. So I'll just put this here. So I'll get 35.72 is equals to 62.5 K parallel R. So 62.5 K parallel R equals to 62.5 K into R. Let's omit K for now. 62.5 plus R. So 35.7 R 62.5 minus 35.72 equals to 62.5 minus, sorry, into 35.72. Anyway, so if we solve this, we will get R equals to around 85 kilo ohms. And this should be the answer. Any doubts in this question?
No, sir.
Okay. Four let us solve later. It is bit, we have to find what we have to find common mode again. Okay, I'll solve it at the last. Let us solve this question. Sixth. Okay. Okay. So anyway, so what do we have to find? Both devices are identical with k this, and further lambda is this much, and I naught is this. RD and RS and everything is given. Okay, so one thing that is missing here in your assignment also, the question is not given. What do we have to find? So you have to find AD. This is a differential gain. Let me write. Find differential gain AD. Please take care of this. I think it is not written in your assignments also for question 6. So else you will be blind like what are these values. So we have to find AD. So anyways, let us try to solve this. To find AD again, let's say uh, we apply plus VD here and minus VD here. Okay. So this and the output is taken here. There is only one output node this time. There is no output node here. Okay. So how this will work is, so when I apply plus VD here, so this the gate voltage of this this transistor goes up. So the current that was flowing, so earlier current ID I naught by 2 was flowing, right? And I naught by 2 here also. Uh, Give me a minute, my pencil is discharged. I naught by 2 flows here also. So when I apply this plus VD here, I naught by 2 plus some delta current will flow here, and when I have applied minus VD here, I naught by 2 minus delta will flow here. So these are the small signal currents plus delta and minus delta that will flow through these branches. So we will do the small signal analysis only for uh, differential gain. So let me write. Okay. So first, okay, let it ID equals to we know GM VGS plus GD VDS for NMOS. So let us do the analysis for this transistor first. So delta equals to GM. GM's that one we have thing we have to see is if the GM will be same. Yeah. So there are only two transistors, so GM will be same. GM. What is VGS? VGS is plus VD minus. So delta current will flow here also, right? Minus delta RS plus GD. GD. So what is the voltage here? Let's say Vx. So Vx will be for AC this will be ground. So 0 minus delta RD. And this voltage, let's say Vs. Vs equals to minus delta. Okay, not minus delta RS. So GD equals to sorry, VDS is VD Vx minus Vx to GM VD minus delta RS plus GD delta so minus delta RD minus delta RS. This is delta. So let us separate delta terms. Delta equals to 1 plus GMRS plus GD RD plus RS equals to GMVD. So delta equals to GMVD by 1 plus GMRS plus GD RD plus RS. So okay, so this delta was flowing here, right? So the same delta in the opposite direction is flowing here. So we can find V out. So what will be V out? V out will be uh, delta RD only, right? The voltage drop here is V out and it is delta into RD, ID RD here. So V out equals to delta RD. Let me take a new page. So V out delta RD equals to, let's say RD versus delta. Delta was GMVD by 1 plus GMRS, 1 plus RS plus GD RD plus RS. So we can find, okay. So what is our gain AD is V out by, since I've applied, so look at here. So I've applied plus VD and minus VD. So differential input is 2VD, right? So the gain will be V out by 2VD. So it will be GMRD by 2, 1 plus GMRS plus GD RD plus RS. So we can find these. So the only thing missing now is GM and GD. So GM is nothing but we just found out 2K ID. So 2K is what? 2.62 milli into and IT is 762 microamperes. So we will have 762 by 2, right? I naught is 762 microamperes. So ID is I naught by 2. So this will come out to be approx 2 millisiemens. And GD will be lambda ID, and lambda is 0.11, and ID is again 762 by 2. It will be, okay, you can solve it. Let me see. I do not have the calculator. 762 by 2.11. It will be 0.0419 millisiemens GD. Okay, and RD is given. RD is 4.9K. RS is 0.7K. So when you put all these values, you should get AD equals to 1.864. So this should be the answer. Any doubt in this question?
Sir, can you show next page? Okay, sir.
Okay. So if not, let us see one more question. So I'll skip the middle question and go to the this question. So it is because a little bit, it seems a little bit challenging and big. So we won't do the complete solution of this. We will do an analytical solution. So how to solve it with quick approximations. So let us see that. So what do we have here? So let us draw. So first of all, what are these different parts? So this is given a folded cascode. So this part is the folded cascode, and what is this part? These are just the current mirrors that are for biasing. This part of the circuit is for biasing. If you see, like, all the voltages are going into the gate, so this is nothing but the biasing part, and this is the actual amplifier part. Is a folded cascode. Okay, so cascode means when we have stacked the transistors one above the other, and folded when we have folded a part of it outside of it. That is why it is called folded cascode. So you have to find the differential gain. So I'll try to solve it. Okay. So if I draw like one side of it, these two are NMOS, these two are PMOS, and this is connected. Connected here. Okay. And this is okay. So these numbers are their widths. So their widths are given. So if you see here, I think it is written. The Kn Kn dash, sorry, is 0.32 millisiemen, and Kp dash is 0.16. So Kp is just half of Kn. So if you see all these transistors, this one, this PMOS, and all the NMOS with 10, so they will have the same GM values, right? The GM is nothing but under root 2k, sorry, 2k ID, right? So if we multiply it by width W by L to W by L, so for L, all the NMOS width is 10, and for most of the PMOS, these and these, width is 20. So these and these all will have same GM that you can calculate. And what about GD? Let's say not call it GD, lambda ID, right? So for GD, these topmost transistors, this one and this one, they have twice the width. It's 2W compared to others. So GD will also be, so for all these transistors, let me not say GD, let's say, let us talk about R naught. R naught equal to 1 by lambda ID. So let if all these transistors will have same R naught, but this transistor, this one, these two PMOS, since they have twice the width, they will have R naught by 2. This and this have R naught by 2. Is it clear till this? Are you getting what I'm saying?
Sir, no, sir.
Not clear?
Not clear, sir.
Okay, okay. Which part can you please tell?
That R not by 2.
Okay, R naught by
When
2 is what?
down. Yes, sir.
Okay, okay, fine. How to explain? Let me take another page. So this transistor has, let's say, these have with W, W, W. It has 2W, right? So, so the current through all these, if this is also W and W, so let's say ID current flows here, and if they are at same bias, let us suppose, so ID will flow here also. So 2ID will flow through this, right? So you can
Yes, sir.
assume it as, let's say, talk in terms of resistance. Resistance is R equals to rho L by A, rho L by length into width. What are you doing for this transistor? You have doubled the width, so its resistance is half, right? So what is R naught? R naught is nothing, just the resistance seen from here, right? So for this for these transistors, this resistance is R naught, but for this one it will be R naught by 2 since its width is twice. Uh, is it
Yes, sir.
getting
Okay. Yes, sir.
okay? Okay, okay. So anyways, so again, we let what we have to find here is this eraser. We have to find the gain AD, and it is again GM Z out. The GM will be of the input transistor we are applying input here. So Z out we have to find at this node, right? Okay, not sorry, output is not here. Output is here. We see this. V out is here. So V out will be the Z out will be seen from here. So what will be Z out? Let us say this is NMOS part. So let us call it Z. Let me number the transistors. 1, 2, 3, 4, 5, 6, 7. Anyway, so Z out will be Zn. Let's say this is Zn parallel with Zp, right? So Zn is what? Zn. So if we solve this, it will be Gm Ro1 Ro2. So I have solved it earlier also. If you solve this, the Z out here for two NMOS with same weight, it comes out to be uh, Gm by Gd square. Or if it is Gd1 and 1 and 2, it is Gd1 Gd2. I have just written it as Gm by Gm Ro1 Ro2. So for these two transistors, this Zn is Gm Ro1 Ro2. Right, write it as Zn only. What is Zp? Zp is uh, Zp will be Gm Ro3 parallel with Ro4 parallel Ro5. Right. Since here, what do we have? We have a branch here. We are going uh, from here. We so let us just say Z out is GM times R out of how whatever the transfer we have stacked. So we went from here. We got GM into RO3. Then there is a branch here. So it will be parallel of these two. GM RO3 into RO4 parallel with RO5. So this will give us that. So anyway, so Zn is Gm. So all these transistors have RO1, RO1 equal to RO2 equal to RO3 equal to RO5 to RO and RO4 equal to RO by 2 that we had just seen here, right? What I was talking about. So Zn is Gm RO and Zp is Gm RO RO by 2 parallel with RO. It will be Gm RO and this will be RO by 3, I think. Yeah. So the parallel of these two is RO by 3. So it will be Gm RO square by 3. Z out is Zn parallel Zp, that is Gm RO square parallel with Gm RO square and AV is Gm into Z out. Okay.
So for Zn, it will be RO plus R1 plus RO2. It will be there.
Where?
Looking into the looking into the source, we should have to have again RO1 plus RO2 impedance. Impedance for Zn. It will be
Are you
GM plus
talking about
G.
this?
Yes, sir, exactly. It will be GMB,
Yeah, yeah, yeah. You're
GM.
right. Yeah. So I have just ignored you. You are correct. So it will be Gm RO square RO2
Plus RO1 plus RO2.
plus RO2. But I have what I've done is ignored it because since this RO or R is nothing but 1 by GD and it is very very large, right? In
Okay.
kilo ohms or mega ohms. So I just ignored this. But yeah, you're right. It will be this. For simplicity, I've ignored this, and but for calculating a solution, you can keep this value. That's fine. But the
Okay.
procedure will be same.
Yes.
I just ignored it for simplicity. Since GM is usually larger than, and R1 or R2, the square will be larger than these. So in this, okay, so in this way you can find this answer also. I have not solved it completely, but yeah, I've just showed you like how to analyze it quickly. Like when you are giving your exam, you won't have time to find exact things. So if you want to do some quick calculation, this is the way. You just look at the widths and consider their GM and GD, and then just multiply them. But yeah, you're right. The more correct way is this only. When you do not ignore anything. Any doubts in this? Uh, should we close the session? Please say something.
Yes, sir. We can close.
Okay.
Done, sir. Thank you, sir.
Yeah. Okay. So I'll just give a hint for question 4 because we have not solved any uh, question related to the common mode gain. So to how do we solve for common mode gain? I'll just tell the method, then you can try it yourself. So for ACN, okay, if this is the circuit, let's say, I'll just take this circuit. So for ACN, what we do is we apply the same small signal on both the. Earlier we were applying plus VD and minus VD, right? But now we will apply the same. If it's plus VD here, then plus VD here also. So what will happen earlier, plus delta and minus delta was flowing here. But this time there will be plus delta in both. And if it is an ideal current source, then it would have resisted these two changes. But since there is an NMOS here, this voltage will change. It will not be ground for it anymore. So we will get some voltage gain. So if we solve the current equations, so to solve this, since now both of these sides are exactly same, we can consider only one of the sides. So it can be something like this. And yeah. So if you just solve for delta, and if V out is here, and if you have VCM here, so if you solve V out by VCM for this, uh, you will get your ACM, the common mode gain. So, and solving it is simple, just using that equation GMVGS plus GDVGS. Okay, so please
And
try
what
it out.
about the resistance?
Uh, okay, so resistance, that's a good point. Yeah. So this resistance is actually what it is doing. It is connecting these paths, right? So to solve for the resistance, what you can do it in two ways. So okay, let me just show it here. So what is the impedance for this? Say it's seen from here. Let's say Z seen from here. It will be, I think, 1 by GM, something like that. I'm not sure. Yeah, it will be 1 by GM of this transistor. Then it is like in a fashion of diode connected. So even if we connect a resistor, if there is some voltage change here, that voltage change will propagate to the gate also. So the resistors will do nothing, but if there was no resistor, let's say there was no resistor, then the equivalent for this would have been RO for here, or RO, or let me say 1 by GD. But now there is this resistor connection here, so its equivalent will not be 1 by GD, it will actually be 1 by GM, GM of this PMOS, so GMP. So that will be the role of this resistor here, this connection. So our gate terminal is, it just means that our gate terminal is no longer uh, grounded. It has something, it will have some AC voltage that is propagating from its drain. So anyways, you guys please try this, and if you feel you are getting stuck somewhere, you can email me or comment in the video also that I will upload. Okay, so should we end today?
Sir, one small doubt, sir.
Yes.
Sir, even though there is a resistance between the drain and gate, so it can
Yeah.
be treated as a diode connected MOSFET, right, sir?
Yes.
Okay, okay. Thank you, sir.
So yeah, because it is doing the same thing, right? It is just propagating whatever changes here to here.
Previous week assignments, ninth question.
Sorry, are you saying something?
So assignment 5, ninth question.
Ninth question, yeah.
Previous assignment, sir. Previous week.
Previous week, ninth question. Sorry. Okay, I will have to open it. Yeah, what is the doubt in ninth question there? Let me see if I have it here. Did I solve that? Okay, I did not solve it. Yeah. So what is the problem in ninth?
In leftmost side, they given us A times I naught, and in rightmost side also it should be B times I naught. Width has been increased.
Yeah, I'm looking at something else. Wait a minute. What is the problem? Let me see. Yeah, so I've solved it. Yeah, what is the problem? GM of the device M1. I answer in my assignments. So this is a current mirror. The current here is B by A, I naught. Okay. Then we apply KVL here. Then we replace VGS by I naught by K terms. And we get this I naught R equal to this. Then what we do is, okay, we'll just solve this equation, and GM of M1 is, okay, under root 2, what I said, IK, right? So this, they have done this. Current is BI naught in M1. And if you solve it, you get this. Yeah. So what was the doubt? Sorry.
I didn't see the calculations. Actually, I thought it should be A times I naught. In right side, in the left side, it was B times I naught, right? Right side also, it should be multiplied by A. That's what I thought. Okay, I got clear, sir.
It got cleared?
I got clear, sir. No problem, sir.
Okay, okay, okay.
I got it. Next question, sir. Next question, small signal gain. How is it, sir?
Uh, the small signal gain I've just found out what GMRL, and for this node RL is this parallel with here, but uh, I've taken it RD only. Okay, so
Then
the
rest
way
of
is this one. It will be GM Z out only, and Z out will be whatever you see from here. So it will be RD parallel with the impedance seen here. So the impedance seen here will be again GM what RO1 into RO2. This, so generally this is much bigger. So RD will be the limiting of these. So parallel of this will be RD. So that is why I've written it as AV equal to minus GM RD.
what about the rest of the current mirror, sir? Looking into it,
So
it should be what will be the resistance?
no, we do not need to look into the rest of the current mirror, right? So the output we are taking, we are only concerned with that node, the Z out here only. So Z out here will be above this and below this. Above this is only RD. Below this is the, okay, how to say,
Only GM.
yeah. So below these are these two transistors, let's say 1 and 2. And this gate of 2 is connected somewhere else, but we do not care about that, right? Because whatever change you make at this node, the gate of it will not change, right? You cannot change gate voltage by changing this node.
Right, sir, yes.
So
So
is it
no
clear?
GMB.
No what?
There will be when it is a diode connected. There will be no GM, sir. Why it's not GM?
It's not diode connected. It is not diode connected. These are two
No, sir.
in
M1.
cascode. This okay. This capacitor does not mean it's diode connected.
No, sir. I'm talking about M1, sir. Here,
M1.
M1 and these above current mirrors.
M1 is diode connected. Yeah, M1 is diode connected, right? But yeah, but we will not consider that because in they are not participating in this branch, right? This Z out here will only depend from these two transistors and this R RD.
Okay, sir.
If it
Yeah.
would have been connected to drain or source terminal, then it would have come into picture, but not with the gate. Gate isolates since no current flows in the gate. Gate will isolate these two branches. If it was, let's say, connected like this, then we would have to consider this also.
Okay, sir. Yes. That's what. Thank you, sir.
Okay. Thank you. So let us close for today. Thank you for joining.